Our energy technology division is focused in these 6 main areas. We started in looking at clean coal and syngas processing work, expanded that into these other areas of carbon capture and utilization, biomass conversion, natural gas extraction and conversion, advanced materials, and industrial water treatment. We focus primarily on this gap of the space between the basic concepts and taking things into the to where industry will pick up the technologies and move them into the commercial space. We partner with public entities, with academia, and with a number of industrial clients. You see some of those indicated below. The EIA still indicates that coal is going to remain a significant portion of the world electricity generation for the foreseeable future. And that doesn't include the chemicals, coal to chemicals and fuels applications that are primarily in China at this time. And even though short term or near term we may see some diminishment in some of the drivers for the need for carbon capture, we still believe that long term global issues are going to drive ultimate reduction of carbon emissions from the use of coal. And to ensure that coal remains competitive in that kind of an environment, current carbon capture costs are just too expensive. They need to come down, and DOE has set some goals as well as to where they like to see that driven. When you look at where the cost comes from conventional means for carbon capture, over half of it's from power. Most of that is from the reboiler duty for the regeneration of the solvent systems that are used. The next biggest hunk, about a third of it's from the capital contribution of the equipment, and about 11% from operations. So when you look at any pathway to reduce that cost, you need to focus, obviously, quite a bit of effort on that regeneration energy, that reboiler duty. What can you do to reduce that? What can you do as well on the capital requirements, looking at things such as efficiency, simplifying the process arrangement, and lower cost materials of construction. And doing this, trying to keep those operating costs in line as well. Here's just a few examples of some of the current state-of-the-art of technologies that are out there. The first large world-scale boiler carbon capture system was the SaskPower Boundary Dam unit that's been operating a little over 2 years now, about 5,000 ton per day of capacity in terms of its carbon capture at 90%. It uses a more traditional shell can-solve amine type process for it. You heard this morning about the Petronova project. In fact, Secretary Perry was there for the ribbon cutting just last week, but they've actually been running since about January of this year. They use one of the more advanced amine systems from Mitsubishi Heavy Industries, what's called their KS1 amine system. That also is about the same capacity of the SaskPower system, about 5,000 tons per day. One of the biggest ones that's out there being not ready yet to capture, I don't think, but it's close, is the Kemper County IGCC project. That will capture almost double the amount, almost 3 million tons per year of CO2 when that is operational. The one thing here is it uses the Selexol system from UOP for the carbon capture, and that has been demonstrated at fairly large scale around the world for gasification for chemicals, mainly ammonia and those type of processes. So really expect that carbon capture technology will work at that system when it is up and running. There are a number of new sort of leading edge advanced technologies under development, a whole bunch of them as you see here. This chart from DOE and ETL. We looked at a number of these ourselves. We think that there are quite a few of them that do hold some promise. The ones most promising to us are the advanced solvents, physical and chemical solvents, solid sorbents, the biomass co-firing, the carbonate fuel cells we just heard about from Fuel Cell Energy, and some of the chemical looping technologies. All these technologies, of course, will take some time to develop and get into the marketplace. RTI has been working a number of years in this area. We have some very innovative solutions ourselves, looking at carbon capture from industrial sources such as fossil fuel power, cement, and chemical facilities. We focused primarily on a couple of areas, non-aqueous solvents and solid sorbents, but we've also done some work in the space of chemical looping systems, membranes, and hybrid systems. We're showing some real progress on those systems with the potentials to reduce that regeneration energy penalty by as much as 50% against monoethanolamine, reduce the overall cost of electricity when you're doing carbon capture by 10 to 12% compared to DOE baseline studies, and reduce the CapEx for that carbon capture block also by as much as half. You can see here on the chart, for example, this is the KS1 amine system for at the Petronova project. This is standard monoethanol amines. This is the kind of regeneration penalty we're seeing for those non-aqueous solvents that we're looking at. This work has been done in partnership with the U.S. Department of Energy, but we've also worked with a number of other government agencies, some of them outside the U.S., such as the Emissions Reduction Alberta, the Gas Nova in Norway, and the Masdar Institute in the Middle East, and also with a number of industrial clients. The solid sorbent process is for flue gas, post-combustion one, is based on an immobilized polyethylene amine in a nanoporous material in a fluidizable condition. That one has shown already potential for a greater than 25% reduction in the cost of CO2 capture, with potential of as much as 40% cost reduction. It has about a 40% energy reduction on that regeneration energy versus the standard monoethanol amines, a high CO2 loading capacity of about 10 weight%, a relatively low heated absorption. One of the problems in a lot of the conventional solvents is they're aqueous based, which means when you're trying to take something out of a flue gas, not only are you capturing the CO2, but you're capturing quite a bit of water, moisture from that as well, which then when you go to the regeneration step and you have to boil that water back out, that's a pretty heavy heat load that you have. This is a 4-year cooperative effort between RTI, Masdar, and Department of Energy that's developed it to the pilot scale, and we've been doing testing now in Norway through this year on the bench scale and small pilot scale system. The status of it is it's ready to go to the larger pilot scale with potential for commercialization in the 2020 to 2025 timeframe. This shows the unit that was done for testing at the Norchem's Brevik cement plant in Norway. That testing was done last year. Most of it's completed, a little bit of it's going on and following up this year. In the phase 2, it has shown the kind of potential that we saw, we're hoping to see for the materials. We've also looked at pre-combustion in terms of sorbent systems and have developed one that can work at 400 degrees centigrade for capturing carbon dioxide from syngas. This one's not as developed as the one I just showed you with the post-combustion sorbent, but it does handle the high temperatures. The experimental work to date on bench scale systems, small pilot, have shown the technical feasibility of the process. The one that we have perhaps the most excited about is the non-aqueous solvent systems that I mentioned. Because they're non-aqueous, it gets around that issue of the water absorption that I mentioned. They also reduce the energy penalty as much as 50% against monoethanolamine. Keep in mind the KS1 is about a 20% reduction that's out there. There's a Hitachi H31, I think it's called. That's about 30% reduction. This is about a potential 50% reduction. So it's really pretty exciting. It also reduces the cost of electricity associated with the capture and reduces the the capital cost significantly. This system is now in pilot stage of testing at SINTEF in Norway. It's a really good cooperation between RTI, Linde, and SINTEF, and with the two government agencies, the U.S. and Norway governments, working together to move this forward and accelerate the technology development. This shows the unit in Norway where it's being tested. It's a large-scale system. It has the ability, we believe, to duplicate and give us a good indication of commercial performance. And part of it is to compare and benchmark against standard amine systems in this unit and then our system. Glad to report that the work to date is the testing has been completed on the monoethanolamine system that showed really good comparisons against the reported commercial regeneration heat loads for the system, which gives us a good indication that what we see from our system will also be indicative of commercial performance. And those initial results are very encouraging. We're seeing the kind of suspected or projected reductions that we were hoping to see, the 40 to 50% reduction in energy reboiler duty against the amine systems. The next step of this will be to actually do a large pilot scale pre-commercial unit in the 1 to 10 megawatt scale. Right now we're looking at that to potentially be done at the Technology Center Mondstadt in Norway, but it might be at the National Carbon Capture Center or other locations here in the U.S. This carbon capture system also has potential for pre-combustion, particularly if it's coupled with a warm gas cleanup system like we showed at Tampa Electric for removing the sulfur out first. And that's one advantage of that technology. It enables other systems that might not have been considered for pre-combustion work to be considered now. The advantage is it's both a chemical and a physical solvent, so it has good performance at low pressure for flue gases, things like that, but as you go up in the pressure for a gasification system, it gives you enhanced potential capacity, almost about a 30%, 25 to 30% extra capacity at the higher pressures that you might see for gasification. I want to just briefly mention an actual demo we did at Tampa Electric Company, funded by the Department of Energy, that used an activated amine system coupled with a warm syngas cleanup system. That syngas clean work was done, finished in April of last year. It's actually now available for commercial license. It involved an innovative process where you have a dual transport loop system that takes a sorbent around that takes the sulfur out at high temperatures up to 600 degrees centigrade. And you can couple that then with back-end carbon capture technologies that you might not have been able to do before. This shows the actual demo site. It was a 50 megawatt demo, handled about 2 million standard cubic feet per hour of syngas. At Tampa Electric, the warm desulfurization process and advanced water gas shift process we also worked on, and then this BASF activated amine process. What we showed was that the warm syngas cleanup did a 1,000 to 1 reduction in the sulfur straight through at the high temperatures. We also demonstrated that the water gas shift used about half the steam that conventional systems have used. And when coupled with the final back-end carbon capture, we saw another 100-fold reduction, so almost 100,000-fold reduction in total sulfur across the system. From this was a petcoke-fired system, so it was coming in about 10,000 parts per million, going out at something less than a quarter of a part per million. The carbon capture system that was employed there was this BASF activated amine system. It was not possible to use this kind of system with pre-combustion systems before because it's non-selective relatively between sulfur and CO2. But since we were able to take the sulfur out at high temperatures ahead of it, we could utilize this system for the carbon capture. The results, the carbon capture process performed as expected. The carbon capture efficiency was 99%, greater than 99%, and we achieved the greater than 90% carbon capture goal that we had. Primary impurities in the CO2 were low. The biggest one was hydrogen, about 1 mole percent. We saw trace levels of CO, hydrogen sulfide, and COS. The combination of those two systems does provide carbon capture with a reduction in levelized cost of electricity, overall IGCC capex per kilowatt, and OPEX per megawatt hour, and a 75% reduction in overall sulfur emissions versus conventional dual-stage Selexol type system. And what we found is that this coupling of the two, when you decouple the two, it enables the overall process of cleanup and carbon capture to be reduced, depending on the system, by as much as 50% in capex, as much as 50% in OPEX across that whole block of the syngas cleanup. Those two processes are actually both now commercially licensable from Casale SA, if there's interest. When you look at the you've captured the carbon, what to do with it when it comes to the storage or use of the carbon dioxide. Safe storage is still being proven. It has been demonstrated now in several places. It does still face some legal and regulatory risks that need to be addressed through various policy measures. But there's some really good innovations in CO2 utilization that may provide some new avenues for beyond CO2 storage. I want to talk about those just briefly. These are all the things that captured CO2 could potentially be used for. The problem is, with all these, you're going up the energy curve from a low energy state to a higher energy state, which takes energy input to utilize that CO2. And about the only conventional technology that's commercially using CO2 is the urea process, taking ammonia and CO2 to urea. But all these have some potential if you had a way to somehow lower that barrier or find another way to offset that extra cost. And that's the approach we've taken. We started looking at some avenues that might offset that cost and still have a substantial, a viable process route. We developed a novel catalyst that actually extracts an oxygen off the CO2 at very low, relatively low temperatures compared to existing technologies that were out there. And it enables then and opens you up for some avenues of oxidation reactions, including things like dry methane reforming and ethylene to ethylene oxide, and that's the one that's actually shown here, where you take ethylene to ethylene oxide, also produce carbon monoxide, which is also a very useful molecule in the industrial space. When you look at how that works, how do you make this viable? If you look at the process for using this catalyst system for the oxidation of CO2 and compare it against the conventional ethylene oxide process, and to make the CO, then you also need a steam methane reforming system or something like it. Where you start seeing the process and simplification is that, one, you don't need the air separation plant anymore because you're extracting the oxygen off the CO2. You eliminate the CO2 emissions from the ethylene oxide process because you're now going to recycle that back to your feedstock coming into the process. You also eliminate the bulk of what it requires in terms of steam methane reforming for carbon monoxide formation. And so when you look at all the pieces of that process that start going away, you find that a couple things. There's one other one. There's a safety thing. The ethylene oxide process has some explosive potential because of high exotherm. But you're now replacing that highly exothermic process with one that's a moderate endotherm. So that helps on the safety issue as well. And overall, you find that at current ethylene oxide processes, this does look like a viable technology. And you also have the CO, carbon monoxide, as a valuable intermediate. And it's able to reduce a significant amount of CO2, almost 3 tons of CO2 reduction per ton of ethylene oxide product, and about 350,000 ton per year ethylene oxide plant to reduce CO2 emissions by about 1 million tons per year. The other thing we like about this is that it's a large volume chemical, so it can consume some significant amounts of carbon dioxide. The closing thoughts. Coal will continue as a key feedstock for worldwide energy, but we believe that there are drivers to still look at carbon reduction from the use of coal. There are several large-scale projects that are out there now demonstrating that carbon capture can work, but to keep it competitive, we believe the costs for those technologies need to come down. There are a number of advanced technologies being developed. You heard about a couple of these today, some of the ones RTI is doing, the fuel cell energy as well, that are being developed and look like they have real good potential for bringing some of those costs down. The safe storage of CO2 is being proven, but still faces, as I mentioned, some legal and regulatory risks that need to be addressed through policy. But these and some of the innovations in CO2 utilization offer some very interesting technology and business options beyond the CO2 storage. That I'd like to acknowledge RTI Energy Technology team, the U.S. Department of Energy, and the other project partners that we've had as we've looked at this.